Hello, everybody. Let's check out this problem, you and I together. It's a nice problem. It has a block that has been pushed against the spring beyond its equilibrium position. And this spring, we don't know what its elastic constant is. The block is 2 kilograms. Then the block is released. So the initial velocity is 0 and the block goes all the way like that, is launched with a certain velocity, we don't know what it is, and goes through a rough patch of friction, and the kinetic friction is 0.03, and the length of this rough patch is 80 centimeters. The object, as you can see here, emerges beyond the rough patch with a velocity 5 meters per second. So it has still enough kinetic energy to keep traveling beyond the rough patch. So the rough patch did not slow it down to a zero. It just has now emerges as an object with a velocity 5 meters per second. I bet it is much less than the velocity when the object was here. Now the question is, how do you solve this problem? The best and easiest way I found is to think about this problem from energy-wise. That's it, energy. Think about it as energy. The object, and divide the problem into two segments. I'm gonna call this segment 1, okay? And this segment here is 2. In segment 1, the object has energy called potential energy, and this is elastic potential energy, okay? All this object's energy now, once released, is transformed into energy to overcome friction or work of friction, and the rest of it is going to be remaining as kinetic energy, okay? So here we have elastic potential energy. All of these energies here, which is the elastic potential energy, was transformed into work to overcome the friction, and the rest of it is left as kinetic energy. So that's how you should think about it. So you can write this equation as this: 1/2 kx squared, because that's the elastic potential energy, is equal to work of friction plus kinetic energy left, or the left kinetic energy. That's it. That's all the problem. If you think about it this way, that's it. You solved it. Okay. Now you have to pay attention. The work of energy here, you don't want to include the cosine theta in it, because we already indicated that as energy was transformed or consumed by the friction work. Okay, so what you have to do is just like as simple as that. You can say 1/2 kx squared is equal to, okay, work of friction is the friction itself, that's the kinetic friction, times d, that's it. You don't need to include cosine theta here, plus kinetic energy, which is 1/2 mv squared. Okay, now 1/2 kx squared is equal to F kappa. We know that by definition is mu kappa times the normal force. N comes down plus 1/2 mv squared. Now what is N? Is the normal force. And if you draw a free body diagram for the object, remember this object is on a horizontal surface, so we know that mg is down and N is up. Okay, friction is going this way, but we are concerned only in the y direction motion, but there is no motion y direction, so acceleration is 0. Then according to Newton's second law, N is equal to mg. So this N here goes to mg. Okay, now 1/2 kx squared is equal to mu kappa times mg times d plus 1/2 mv squared. 1/2 comes down, the elastic constant comes down because we're looking for it, x squared, which is the compression in the spring beyond its equilibrium squared. So that's 10 centimeters. We need it in meters, so it's 0.1, and that's squared. Now mu kappa is equal to 0.3. M is 2 kilograms, 9.8 for G, and D is 80 centimeters, which means it's 0.8 plus 1/2 times the mass of the object. Again, it is 2 kilograms. And the velocity as it emerges from the other side is 5, and that's 5 squared. Okay? Okay, 2 with 1/2 goes away. 5 squared is 25, so I can put that here. Okay, and this number you can calculate it with calculator, and it's going to be equal 4.7, and this number comes down as 1/2 k times 0.1 squared is 0.01. As you can see, the only unknown is the elastic constant. With some calculations, you can find out that the elastic constant is equal to 5,941 Newton per meter. Now, the physics behind this problem, again, is energy. Think about it from energy-wise, okay? Energy stored in the elastic spring in a form of elastic potential energy has been transformed into two types of energy: work to overcome friction plus kinetic energy. That's it. That's what's all left. All this has been spent into this plus this. I hope this helps. Thank you.